Hello everyone, my name is Anupam, and today I'm here to introduce a project where we try to teach robotic policies, especially VLAs, where to look using human gaze supervision. In a manipulation task, right, the robot receives a full image, but the action often depends on a small number of task relevant regions: the object to grasp, the target location, or maybe the contact boundary. The issue is that action supervision alone asks the policy to solve two problems at once: discover where the important visual information is, and then learn the correct action from it. For example, in this simulated task below, for a given task of picking up the bowl, attention to the whole image is not really necessary. Only certain regions of the image are informative. In the case of the current VLAs, the language conditioned visual attention is very diffuse and all over the place. So when humans perform manipulation, the gaze is not random. We look at the object before grasping it and then at the target before placing it. So essentially gives us a window into task relevant perception. As a small example, we can see how human eye gaze does not look at the whole image, but only certain task relevant regions. The task is to pick up the tennis ball and place it into the container. First we try to spot the tennis ball, and once we grab it, we try to spot the container. So the key research question is that can we use gaze as a training time auxiliary signal to improve grounding in VLA policies without changing the architecture and without using gaze during inference. Our idea, like I said, is to use gaze only as a training signal. During training, gaze tells the model which visual patches are likely to matter, and hence we use gaze as a soft attention prior. First, we convert gaze into patch level supervision, then we align internal model attention with gaze, and this way the policy interface remains unchanged during inference. First, we utilize a third-party gaze prediction module to predict gaze heat maps for the images. The GLC model, as mentioned, takes in a sequence of images and thus gets a global context and predicts the gaze heat map. Because manipulation unfolds over time, we do not treat gaze as a single frame saliency map. We aggregate nearby gaze heat maps so the signal captures both current fixation and some short-term anticipation. Once gaze is obtained, we then map gaze from pixels into the same patch grid used by the vision encoder. This gives us a probability distribution over visual tokens, which then can be used to align internal model attention with this newfound gaze distribution. A key practical advantage is that the gaze is only used during training. Once trained, the policy runs with exactly the same inputs as baseline. Across two sets of simulation benchmarks, the Libro suit and the Aloha simulation, we observe that our gaze-regularized model outperforms the baseline model without gaze consistently. The previous experiment was conducted using Pi0 as the backbone. However, when we use OpenVLA as the backbone, the trend of the gaze-regularized model outperforming the baseline model still exists. When we analyze the effect of the regularization strength, we observe that when the coefficient of lambda is set low, the performance is the best, indicating that gaze should be used as a soft attention prior. And finally, to conclude, VLA models need selective visual grounding for manipulation. Human gaze provides a task-relevant attention prior, and at the end, training time gaze regularization improves success while preserving gaze-free inference. The broader message is that human perceptual behavior can supervise robot learning. By teaching policies where to look during training, we can improve where they attend as well as how they act. This concludes my presentation. Thank you for your attention, and we are always open for discussions and potential collaborations.